So I would like to thank the organizers for this nice conference and the beautiful program. I enjoyed it a lot. So today I'm gonna talk again about defects. So it's the third talk about dynamical defects today. And I'm gonna talk about how it can interplay with symmetry and what constraint symmetry can give in the IR of these defects. So this is work that appeared in December with Andrea Antinucci, Giovanni Galatti, and Giovanni Rizzi, and there will be and there will be more work to appear, so hopefully soon, but I will not put a date because it's really, it never works out for me. Okay. And yeah, so okay, let's go on. So both Ifan and Ingo gave a very good introduction about defects. I'm going to go quickly through this. So why am I interested in defects? So they are very ubiquitous in physics. They come out in a lot of different circumstances. For example, in FTH, they can be Wilson lines or Toft operators, pinning defects, as we saw today, or domain walls, monogamy defect. There's a lot of, and they've been studied by a lot of people already. So I couldn't really put a good list of references, even because I don't really know all the references, just a very wide field. It's also in condensed matter, if you think about impurities like the Kondo problem, they've been around for a very long time. And here also there are a lot of variation that you can do. And people have thought about this a lot. And if you really want to be a bit, you know, you can also think that generalized symmetries are topological defects, or a particular case of defects, no? And you can come up with more examples. So this is really like a huge class of things to study. And why we like it is that you can think about using them as probes into strong coupling dynamics. For example, as you can use Wilson lines to prove confinement, to probe confinement. But the problem is that this system tend to be strongly coupled. So it's really hard to give any concrete prediction in more than 1+1D, and apart from Lagrangian action expansion techniques. So there's a lot of work to do. So let me just go through quickly how I think about defects, just, I don't know, to fix your ideas. So you can define them as electric defects, by which I mean you have some bulk Lagrangian, and you couple some matter on the defect wall volume with some coupling. And there are many examples like this. So if you think that the matter is trivial, this is a bit like the pinning field. And Wilson lines are inside this category. You can think of the OM defects, so like the pinning field defect, which is this one up here, and so on. So this is like a huge category. You can have magnetic impurities. So this just means that this is your defect wall volume. You do a cylinder around, you cut an S d minus p minus 1. P for me is always the dimension of the defect wall volume, space-time dimension. And you prescribe boundary conditions on it. This is another way to define a defect. And you path integrate. So, for example, Toft operators are defined in this way. But sometimes you can have a different description for the same thing. So it's not like one-to-one, but just to have an idea. And in condensed matter, people think about impurities. So you have a lattice system, and you just change the degrees of freedom at one site or a few sites around, and you can study the physics of the impurity. This is like a Kondo problem, for example. And you can come up with other ways to define defects, but it's just to fix a bit what I have in mind. And I think most of the talks I will think about electric defects mostly today. And what you do with them? Well, we do G flows. So the idea is that in the UV you have defined the defect in some manner, and you want to know what happens in the IR. And there are some scenarios that also Yifan mentioned, so I will mention it again. So what I will call screening is when the bulk and the defect will decouple completely. So this is a bit of terminology. There is no complete agreed notion of screening, but this is mine. So as far as the bulk is concerned, the defect acts like identity. There can be like decoupled quantum mechanics, decoupled CFTs, but this I would call screened. This is just my name for it. I know that people don't agree on it, so it's just a name. It can be conformal, so you can preserve the conformal group on the defect wall volume times the rotations. This is a possibility, and people have studied this quite a lot. Or it can be topological. So for me, topological means that it's topological and acts non-trivially on the bulk degrees of freedom. So there is a faithful action of the defect on other degrees of freedom, which is different from screening. This is my terminology. And in some cases, it can also be runaway, which means that the RG flow doesn't stop. The coupling goes to infinity. But this, as far as we know, is expected to happen only for free bulk theories, because if you have bulk coupling, it will stabilize the beta function usually. It's not a theorem, but is what is expected. So in most of the example, I will not think about the possibility of runaway behavior. Okay? So for this talk, I will consider the case in which the bulk has a symmetry, which I denote by C. It can be
confining theory, where does it fit?
Well, I think if you think about it in the confining theory, I think it's screened.
It's considered screened or not?
It's not because the value is 0, no?
Yeah.
Yeah, that's a good question. I think the defect is so yeah. Maybe instead of saying that it's the identity defect, you can say that the correlator of correlation function of bulk operators in the presence of defect factorizes from the defect, and then I think it covers the Wilson line.
Okay, so you just fit it into screening.
Yeah. So this is a bit schematic.
Value, like
yeah, I think the best definition that I know is if you consider correlation function of operators in the presence of defects, is like the correlation function without the defect times the defect one-point function. That's like I think the best. Then it's more precise. But yeah, it's hard to make it very sharp mathematically. My impression about screening. If the theory is I think so. So, but if the bulk is conformal and you have a screen,
you assume always the bulk is conformal, right?
The examples will be about that, but the constraints I will talk about don't need to assume that.
So then RG is both on the bulk and
it can be. I will talk about this now. So yeah, now I think now. So like the common setup, which is okay. Sorry. So I was saying that in this talk the bulk has some symmetry, which I refer to as C. It can be some non-invertible symmetry, continuous symmetry, just a name. And we want to use it to constrain what happens in the IR of the defect. So we want to rule out some of the scenarios. And usually what people have studied in like 99% of the literature is that the bulk theory is fixed, a CFT, and the defect flows. And this is called the defect LG flow for me. Okay? But these results that use symmetry can hold even if the bulk flows and the symmetry is preserved, as long as we assume that in the IR the symmetry acts faithfully. This is the caveat. If the symmetry does not act faithfully, you have to look at it and see if you can say something or not. And usually no. Okay. So this is the setup. Any questions about this?
Just to clarify the assumption, faithfully along the RG means still faithful in the infrared?
Yeah, in the infrared. So for example, it can be that the bulk theory goes into a trivially gapped phase, and it's not very constraining. And it will come up to the fact that if the symmetry is not faithful, you can cut it open by topological defect in the deep infrared, and this will invalidate many of the kind of things I will say. Okay, so let's go on. So I just prepared a map for the talk. So this is the defect LG flow. Then we will have symmetry. And then we will have a symmetry action. In the UV and the IR is the same symmetry action. So mathematically, this will correspond to some type of module category over C. And you have to put some adjectives depending on the dimension, the type of defect. So this is just a rough idea. And what I want to discuss are two things. So can we describe new classes of conformal defects if we impose symmetry in the UV? And can we put constraints on the screening, on the infrared defects? These are the two questions I want to talk about in the talk. And there are some related comments in a paper I wrote in August, and in the paper by Brandon, Yichul, and Yoonjin. So you can also look at those papers if you're interested. And I made a representation of the defect LG flow. ChatGPT made it, so this is the defect LG flow. I also have an explanation, but I will skip it. Like it makes sense. Okay, now let's go on with the talk, no? So, first I have to tell you what I mean that the defect is symmetric, so I have to give you some definition. I think Ifan already mentioned it, so I will be kind of quick. So we will fix G equal U1 in this slide. You can do the same for other symmetries, but this is just to be concrete. So if you have a continuous symmetry and a defect, the world identities for the current get modified usually. This is actually quite a recent result, but people study defect for a long time. This was very surprising to me. And this is the modification. So this T of X and this delta is just a delta function localized on the defect world volume. This T of X is called the tilt operator for historical reason. If you want to know, ask me. And what it does, if it's a non-trivial primary, it signals the breaking of symmetry by the defect. So if the tilt operator is non-trivial, the defect is breaking the symmetry. So if you want to preserve the symmetry, you have to make it trivial. It has to be descendant. So what will happen in practice is that it will be the divergence of a current that lives on the defect. This maybe we can call defect current. And when this happens, this is done in the UV, so there is no conformal symmetry here on the defect, because conformal symmetry will forbid this. When this happens, I will say that the defect is symmetric, okay? This is just the definition. Then let me tell you what it implies. So if a defect is symmetric, you can improve the symmetry generator. This is the symmetry generator for the U1 symmetry in the presence of the defect to this guy. So you see I've added some integral of the current on the intersection between the defect and the bulk. And if you do the improvement, you assure that this new operator, that now the hat will disappear, but it will always be assumed that it's this guy, is topological even in the presence of the defect, which is what you expect. And what it means is that it commutes with the defect in practice. But you can also talk about disjunction, which gives you some more power over the representation theory on the defect. So to be short, symmetric means that it commutes with the symmetry defect. Okay? Good. So let's go on. And yeah, when you have a symmetric defect, you can do many things that you like from high energy physics. You can turn on gauge fields, you can talk about anomalies localized on the defects. So you can play many interesting games. But let's go back to our talk. So if a defect is just symmetric, you don't have strong constraints on its SLG flow, especially on the problem of screening. This is because the identity defect is itself symmetric, so there is no contradiction for the defect to be screened in the IR if it's just symmetric. So you need to specify more stuff if you want to derive constraints. So you can think of this as like specifying a complete representation of the symmetry and the defect. It is some modification of this concept of strip algebra that has appeared in many works, also in the last year especially, and also connects with the concept of generalized charges or higher tube algebras of some kind that appeared in this work. And there is also a mathematical framework that I think is factorization algebras that contains this, but I'm not an expert, so if you ask me, I will just tell you the name. So you can, if you do this, you can talk about many interesting things like defect anomalies, and you can encode this in a symmetry TFT, but this will not be for this talk, but there is a way to do it by considering a sphere reduction of the symmetry TFT. So there is a way, if you like this technology, to talk about this. But now we focus on one particular representation of symmetry and a defect for the rest of the talk. And this we'll call symmetry reflecting defects. So this is what it means. So it means just that the symmetry operator is absorbed by the defect. And like this is very much related to the concept of strongly symmetric boundary condition that appeared in this paper if you do folding for codimension 1 interfaces. So you can rephrase the things. But this is stronger than the commutativity. No? Now the defect can be absorbed by the world volume. And I will just talk about interface for the talk, just because it's easier to, it's more concrete. You can do it for the higher codimension, but you have to be a bit more careful, and it will become a bit messy for half an hour talk. So for codimension 1, G continuous, it just means that the pullback of the current on the defect is J-perp, just a perpendicular component, is trivial. So it's a total derivative of some other defect current. You see, this is not the same as the previous equation for the symmetric defects. It's the same only for boundary conditions. So for the boundary conditions, there is no difference. but for the defects, there is a difference. And it's an important difference. And yeah, alternatively, you can think that the defect can terminate topologically on the symmetry defect can terminate topologically on the dynamical defect. Okay? And what are the consequences? This is like a very simple thing. You can derive some consequences very easily. The first is that this symmetry now acts independently on the two sides for interfaces. So you have two sets of all identities. So you can just, bring the operator in from infinity, pass it through the charge stuff, and then it hit the interface where it will disappear, and it's consistent only if the total charge is 0. So you can do the same on the right. So the symmetry is really the double, and you have more world identities to play with. And if you want to think about scattering, like you take something, you throw it on the defect, and you say what it means. It means that if you are a charged object, so you scatter a charged particle, it will always come back, so it will be totally reflecting. So for a charged object, this is like a hard wall. It's like the factorized interfaces that Ethan talked about. Actually, this is like a natural setting in which you find them. But there are examples in which this happens and they're not factorized. So the reflection coefficient is, for the full thing, is not 1, but is 1 if you restrict to charged subset. And you can also replace this using the defect OP if you like the language more, but this I liked just for the talk. And second consequence, which is what the talk was about, is that this cannot be screened in the IR. So it's very easy to prove. You just draw a picture, you think that this becomes a trivial defect, and this implies that there is a topological termination of the symmetry defect, which was my assumption, that the symmetry is faithful and this cannot happen. So then, if this is true, this defect cannot be screened in the IR, and what are the possibilities? Can be a non-trivial conformal defect, can be a non-invertible topological defect, can be condensation, but must be non-invertible, or it can be a theory of Goldstone bosons. So like what Ethan said today, this is also a possibility. And so, let's see, how much time do we have left? 10 minutes, okay. So now you say, okay, you've given this construction, but who cares? There is no example, so it's just a formal thing. So now I want just to show you some families of defects that you can realize in the UV and have these properties, and then you can think about the RG flows. No? So the rest of the talk is about this. So if you have any questions, this is like a good time to stop. Okay, no questions, so let's go on. So I have 3 constructions, so we'll see how much time it will take, and I can cut the rest. So the first is what I call coupling via 't Hooft anomaly. So the setup is the following. I consider G equals U1, just for concreteness. There are other cases. This is the simplest. And I consider surface defect, P equals to 2. Okay? There are some generalizations, but they're not quite as nice. And for the defect in the UV, I take a surface on which there is some matter, which also has a U1 symmetry. But this symmetry has a 't Hooft anomaly. So in practice, this is the equation. And F equals dA is just a gauge field for the U1. No? This is pretty standard. And now what I want to do, this equation seems a lot like the equation I had before, but I just need to substitute F for the J perpendicular. No? So if I can find a way to do this, I automatically define a symmetry reflecting defect in the UV. And the LG flow will be always with this property. So there are simple ways to do it. So for example, if you have a compact scalar on the defect, then you can just turn on some kind of theta angle. And this gives you already the property in the UV. And it's nice because usually you think, if I gauge a symmetry with a 't Hooft anomaly, I will break the symmetry, no? But if you gauge it on the defect, you actually make the defect interesting. You don't break the symmetry, but it will be represented in an interesting manner. It's a nice kind of shuffling of concept. And you can use this to construct an interesting example of defects that cannot be screened in 2+1D and 3+1D gauge theory, especially if you have a U1 topological symmetry, no? And then, of course, just this J-perp is just dA. So it's what you expect, and this is just the theta angle on the defect. It's just gauging the symmetry on the defect. And these are, like, as far as I know, are classes that have not been studied. So you should try and see if we know they are non-trivial in the IR, but I don't know what they are. So we have done some examples, like in Maxwell theory, there's a theory of Goldstone boson, but you can do better. It's just not very easy. So this is one class of examples. So another class is related to what Ethan was talking about today, to the pinning field, and is about deforming topological defects. So you can also see our paper and Yifan's paper have examples of this, and there is also all the literature. So the idea is that this is the pinning construction. You start with identity defect and you deform by a relevant operator. But what you can do, and this is symmetric if the defect commutes with the symmetry, no? But you can do the same, but you start with a topological defect n, which absorbs the symmetry in the UV. So you disimpose in the UV. That can be the duality defect of Tambari-Yamagami, for example. And then you turn on some operator on the defect. So there are two cases. There are some cases which are not very interesting, but there is a class of interesting cases in which you can turn on a non-local operator. So here, for example, it can be in a twisted sector of some symmetry operator that can end on this n. So this you can turn on the defect. If it's neutral under the action of n, you can turn it on without regulating, just on the defect, otherwise you have to specify some regularization. And this is a very good RG flow. So you can look at this. And this is just the commutation relation here. So there might be some quantum dimension factor I wasn't careful about. This just means that this L is the symmetry I want to preserve. This just means that this doesn't break the symmetry. Makes sense. And you can try to see what happens in the IR. So, and nice thing is that you can use non-local operators to do this. So there is a longer list. And this has already been studied years ago. As always in CFT, there's like people did this a long time before, and then they discover things. And the simple example is Ising CFT. That's always the example. And there's a line I will take 1 plus eta. So it's not a simple line, the UV. And I can turn on the mu deformation. So the mu deformation you cannot turn on locally, but you can turn it on 1 plus eta because it absorbs the eta line. This is like a good RG flow. And you can ask what's the end of the RG flow, no? And it's easy to bootstrap actually what happens. So you can consider what happens if I take a product of the Kramers-Vannier duality defect with this deformation in the UV. And you can convince yourself that this equation holds. So you just deform by sigma, which is mu becomes sigma, but twice with the different signs. And this deformation is known, so you can just flow in the IR. In the IR, this will flow to this, and this will flow to this. These are the Calvi states for Ising. And then you solve this equation. So you plug it in, you multiply by n, and you find the solution must be this. So this is a factorized defect, as you expect. This happens often, but you can kind of bootstrap with the symmetry. And there's examples in all minimal models. You can make many of these. And Yifan has a different derivation of this in his paper, so like you can do it in different ways. Okay, so I also have a third example that I think it's nice, which is slab gauging. This works for continuous symmetries. So, you know, people studied a lot gauging in Alt spacetime of discrete symmetries to define duality defects, and so it's some interesting history. But you can try to do it for continuous symmetry. Then you turn on the gauge field kinetic term, and the thing is not topological. You can still define some good conformal defects like this. So you can take a slab of length L, and in the slab you turn on a gauge field for the level symmetry of the model. Then you can ask, you float in the IR, and you ask you look for very far away and you see a defect, and you ask what is this defect? It's a legitimate question. And so you have to perform some defect fusion. So in the IR there will be something inside here, some IR theory. You have to perform fusion of these interfaces. There will be some divergent term, and you can consider this defect here. And since you have gauge symmetry in the bulk, you are sure that this is symmetry reflecting, because this operator inside will be trivialized by the Gauss law. So this is a set of nice examples, hard to study, but you can, so there is some lore that you can have. So depending on what you have inside in the bulk, if it's a gap theory, this will be some factorized interface, and if it's a TFT, it will be not simple, but direct sum, as Yifan told us before. But if it's a conformal theory, chances are this is a simple defect which is not factorized, so there will be non-trivial reflection and transmission coefficients. And might be something new that people didn't study. So an example that you can work out, because people already worked out the ingredients, is WCW models, 1 plus 1D. So you can take G level K, and you can gauge the vector symmetry H inside the slab, so the one which is anomaly free. And then you know that, well, this is like a conjecture, but in my opinion, it's like a true conjecture, that the IR fixed point is the coset. And this is the coset with the universes, not the coset with the single thing. But you can also get the coset with a single thing if you gauge some quotient of H. So some technicalities. But I will take this as a true conjecture. And then and then you can think of this as a Dirichlet boundary condition here and here. And you can convince yourself that for this interface, it's labeled by a doublet. One is rep of the coset, one is rep of the subgroup. So it corresponds to the fact that I can put a fill in the line for the coset inside here. This can go here and here. I just put it here by. And you can put a fill in the line for the subgroup here, which will act here non-trivially, because here it cannot exist. And if you have the interface is labeled by a triple, so you can do this. It's the same, but now I have only one line here, because I can only put it once, but two on this side. And then you can ask, okay, does it match in the AR? This is like a UV point of view. I just use the symmetries here and here and here. But does it match in the AR? And people have constructed these interfaces for the WZW models. So you can look at this special case and count the number of labels, and it's the right number. And then you can ask if you can do defect fusion and compute the defect. I mean, this I didn't do yet, but I think it can be done. And this is like another case in which you have a set of examples, and symmetry gives you a lot of power already to think about what is possible to happen. And another nice thing of this construction that people didn't realize back in the days, that you can also use symmetry to reveal that there are some hidden theta angles on these defects. This is just because when you gauge, you will, like for the simplest example is SU2 mod U1, because when you gauge U1 vector, you will have U1 vector times U1 axial in the symmetry to commute with it, and the U1 axial is anomalous. So what will happen, it will break on the slab, and this is like a theta angle for the defect. So you can think about, well, there are two, there are one on the left and one on the right, and this is like a nice feature of this, which you can derive by symmetry. So there are many considerations like this. And this is just maybe the starting point. So like people starting to think in this way, and hopefully we can have like stronger results in the future. So with this, I thank you, and I just leave a slide with the open question. You can ask me about it. I'm happy to tell you what I think about it.
Going back to your WZW example, I wonder if you've thought about making defects in coset CFTs directly, not just in G level K, and if they have something interesting to teach us about 2D QCD?
I think so. There's a class that essentially is in two papers. There's a paper by Quella and Schomerus, and a paper by Quella and Runkel. This paper that computed the fusion. And there is a class that you can describe well if you want to preserve some chiral algebra. This is known. And you have pretty explicit formulas for some quantities. So those are kind of under control. And it was in this class. So I was lucky. But in general, it's pretty hard to construct them. But I think if you have some other symmetry consideration, maybe you can say some things. So it will be nice. It's just that we are still learning how to use symmetry effectively to ask questions about defect RG flow, in my opinion. So some things are not as sharp as they could be. I think in particular, there is a concept of having an anomaly on a defect, which makes sense, no? And it's, I think, a bit related to the concept of transmutation we saw yesterday. If you have enhancement of symmetry, it's like a generalization if you have something which is not a line. And this kind of matching has not been studied a lot, but in 2D you can make it very explicit. So I think that could give you something to work with. Then, of course, it is usually discrete symmetry, so you cannot really completely fix an answer, but maybe you can say something interesting.
I have a question. So you were saying that it's important that the G symmetry acts faithfully in the IR, because otherwise you can trivialize these defect operators, and then the statement's sort of meaningless about that you could absorb into a defect.
Yeah.
So I guess my question is if you've thought about sort of more general G actions, because as we saw in Sahan's talk yesterday, you can have the action of junctions, or you can have hired codimension intersections that could also potentially act.
Yeah, definitely. So you can derive some constraints. I'm just saying that they will depend on the transmutation of the symmetry, is the name now. So it's how the symmetry will act in the IR. So if it's faithful, I know to say something very concrete. If it's not, and you have some other thing going on, you have to look at the case. But yes.
It's not going to be as powerful, you think?
It's going to be probably less powerful, but it's going to be useful.
Okay, cool.
There are cases in which it's completely trivial, so it's not going to be useful at all, but there's going to be some power. I'm just saying that our paper doesn't cover this, so people need to think about it.
It's a very naive question, but in 2D, and there is this recent conjecture about conformal interfaces where the effective center charge given determining the integrable entropy should be no less than the two-point function of stress energy tensor on two sides. Do you think we can use symmetries or some other method, and it's for some special class of defects or interfaces that we can make progress on proving this conjecture?
I think it's hard using symmetries, just because discrete symmetries don't value that much. Right. But I think you can, I mean, what is what I wrote here, you can try to do the symmetry refined version of these objects, and then you will see how the defect, the representation of symmetry on the defect impacts the entanglement entropy across it. So there are simple results you can state, like if you have this symmetry reflecting, and you resolve the entanglement entropy, you will get 0. So, but you can do better, so this is just a stupid thing. But if you, that bound is more about the stress tensor, and the symmetry doesn't see the stress tensor. So if for WZW, you can say things for sure.
Do you think maybe there will be a bound for a current two-point function?
Yeah. So I think you can do something like that, and then if you do WZW, you can use Sugawara and derive some constraints, but in general, you're missing a sector, which is the neutral sector, which is important for these bounds. So it's...
Thank you.
Is there anything you can say in general about the fusion of this symmetry reflecting defects?
I think this is an interesting thing. So, of course,
it has to be symmetry reflecting in the end. Yes, that's
but there are various ways in which this can happen. So, like let's think about Z2. No, so they're a bit concrete. So it can be that the leading term in the fusion is indecomposable and is symmetry reflecting, but it can also be a doublet. No. So you have constraints, but they're not super powerful, I think. I think they're interesting, but I didn't find a way to make them...
So do you know how the degeneracies may come out from properties of the symmetry?
That's a good question. No, I don't know. Mm-hmm. But that's something that I think you should study. Also, there's this notion of anomalies on the defect, because these also should match on the fusion. So if you put these together, I think they become strong, but people didn't explore it yet. So I thought about, So for example, the bicharacter of Tambari-Yamagami is a bit like an anomaly on the defect, and you can do similar things, no?
Okay, well, if there's no more questions, let's thank the speaker again.